We're now going to do a fairly extensive analysis of the following system. We have a 12 kilogram mass attached with a string over a pulley to a 3 kilogram mass. Gravity acts on the 3 kilogram mass to pull it down. We assume there's no friction anywhere in the system so that the pulley doesn't slow the thing down. The rubbing of the object here over the tabletop doesn't slow the system down. We assume an initial velocity of 0, and we ask what happens as the system descends 2.9 meters. That is, as the 3 kilograms descends 2.9 meters, as the system moves 2.9 meters in what we'll call the positive direction, this way. First question, set of questions. What's the net force, the final velocity, and the string tension? Okay, we can do a force diagram. We see that we have a force mg, g being the acceleration of gravity, m the mass of this object. The mass is 3 kilograms. Acceleration of gravity is 9.8 meters per second squared, giving us a net force of 29.4 newtons on the system. And we say this is the net force on the system because the sum of all the other forces in the system is 0. Specifically, we have the weight of this object. We've just calculated the weight of the 3 kilograms. We could calculate the weight of the 12 kilogram object, but it's sitting on the tabletop, and presumably the table is strong enough to support the weight, and therefore exerts a normal force opposite to the weight that cancels the weight. So now we can see that the system has a net force of 29.4 newtons acting on it. The system has a total mass of what? 12 kilograms and 3 kilograms. We've implicitly assumed that the pulley has negligible mass. Okay, so 12 kilograms and 3 kilograms gives us a 15 kilogram system mass. A net force of 29.4 newtons gives us a system of acceleration. We simply divide the force by the mass. We get the acceleration 1.96 meters per second squared, from which we can use one of the equations of motion to find the final velocity as the square root of the square of the initial velocity in 2a delta s. We just plug the initial velocity, which is 0, the acceleration, which we just found, and the displacement, the 2.9 meter distance through which the object falls, into this, take the square root, do the units carefully. We get, I think, 3.37 meters per second. Okay? So that's the acceleration of the system under the given conditions. Now we want to find the tension in the string. In order to do that, let's isolate this 3 kilogram mass. The reason we isolate it is we know the force of gravity on the 3 kilogram mass, and we know that the tension is opposing gravity, preventing the 3 kilogram mass from accelerating downward at the rate that it would if the string wasn't there. Now, the net force on the 3 kilogram mass is then the 29.4 newtons. We'll assume that downward here is the positive direction, minus the tension. Okay? Now the net force on the 3 kilograms is also 3 kilograms times 1.96 meters per second squared, because the net force is nothing but the mass multiplied by the acceleration. So we see that the 29.4 newtons minus the tension has to equal the 3 kilograms times 1.96 meters per second squared. We can solve for the tension. Solving for the tension, we could add tension to both sides. We could figure this out. When we multiply this, it comes out 5.9 newtons, so we could subtract that from both sides. You can go through the algebra details, but we get a tension of about 23.5 newtons. And again, this is because the actual acceleration is 1.96 meters per second squared, and not 9.8 meters per second squared, as it would be if the string wasn't there. Now, we want to find the work done by the net force and the final kinetic energy. Well, the work is fairly simple. We know the net force, 29.4 newtons. We know that the system has a displacement of 2.9 meters. We immediately find that the work done by the net force is 85 joules. We determine then that the final kinetic energy is the initial plus the change in kinetic energy. Change in kinetic energy is nothing but the work done by the net force. So that the final kinetic energy is going to be the initial plus that work. The initial kinetic energy is 0, the work is 85 joules, so the final kinetic energy is going to be 85 joules. And now we want to find the final velocity from the final kinetic energy. Well, 1/2 m Vf squared, if Vf is the final velocity, is the expression for the final kinetic energy. This expression can be solved for Vf, multiply by 2, divide by m, and take the square root of both sides. And we get this expression. We can plug in the 85 joules for the final kinetic energy, 15 joules for the 15 kilograms for the mass. And when we take the square root, using the units carefully, we get 3.4 meters per second. And that'll be the final velocity as determined by the kinetic energy. And of course that agrees well with the 3.37 meters per second that we obtained from the equations of motion. The energy formulation has to be absolutely consistent with the equations of motion, since in a sense the whole concept of energy comes from those equations and from Newton's second law. Now we ask, what's the change in the gravitational potential energy of the system? Well, the decrease in potential energy, in gravitational potential energy, is the work done by gravity on the system. So when gravity does positive work on the system, the potential energy decreases. When gravity does negative work on the system, the potential energy increases. Okay, the change in potential energy is then the negative of the work done by gravity on the system. Since the decrease is equal to the work done, the decrease is the negative of the potential energy, which equals this, so this equals the negative of this. And that can also be seen as the work done by the system against gravity. I had on gravity, just following the phraseology we used here, and decided that I wanted to change that to against gravity. We'll note that the gravity and the displacement of the 3 kilogram mass are parallel, and it's the 3 kilogram mass whose potential energy changes. Gravity doesn't do any work on the other mass because the other mass doesn't move in the direction in which gravity acts. Gravity acts downward. So something that moves in the downward direction, gravity would be doing positive work on that object. If it moved in the upward direction, gravity would be doing negative work on the object. Okay, so the work done by the gravity on the system, we very quickly calculate to be the 2.9 meters times the force exerted by gravity, 29.4 newtons, or 85 joules. So the change in potential energy is negative 85 joules, and we note that the change in potential plus the change in kinetic energy is 0 in this case. Now that's going to be true in this case, or in any case where there's no force but gravity. And again, I guess we should be specific. This is gravitational potential energy, and that's all we're really talking about here. So that the gravitational potential energy change plus the kinetic energy change is 0 if gravity is the only force acting on the system. And that's something to kind of store away. We're going to be dealing with these ideas in a little more detail shortly.